Okay, so here's a worked example for myopia. Okay, now this is the worked example from the book. It's from page 122. You may call me a lazy teacher, but I don't care. So what have we got? A girl's near point is 25 centimeters from her eye, but her far point is at 400 centimeters. From what defect of vision is the girl suffering? Okay, well, if you think about it, if you put yourself in the girl's position, so she can focus on things from 25 centimeters up to 25 centimeters, or from 25 centimeters on out, but her far point, the furthest distance at which she can focus objects, is 400 centimeters. So that means that her near vision is good, but her far vision is poor. Okay, so therefore she is good at short distances and bad at long distances. So she is short-sighted. Which is to say she has myopia. Right, that's mark 1. Now, what type of lens should be prescribed to help her see distant objects? Well, it might help to refer back to your diagrams at this point. Okay, here's the diagrams for myopia. So when you're myopic, here's the problem. Parallel rays from an object at infinity get focused before the retina, and therefore you see a blurry image. So it's like the eye lens is a little bit too strong. So it produces the image before the retina, and therefore you can't see it properly. Now, how do you fix it? Well, if the eye lens converges the light too much, what you need is a diverging lens to diverge the rays a little bit so that they actually meet up on the retina. So you need a diverging lens to correct it. So what type of lens? She needs a diverging or concave, if you prefer, lens. Either will do for the mark. Okay, so far so good. Now, what is the power of this lens? Well, power is the reciprocal of focal length. So to find the power, we need to find the focal length. Now, let's just go back and review again, and this might help. So, to correct short sight, what you need is a diverging lens. Okay. Now, what the eye can do is, if the far point is, if you have an object much closer to the eye than infinity, then the eye can focus those rays on the retina. So the actual far point is much closer to the eye, and in the girl's case it's at 400 centimeters from the eye. So what does the diverging lens do? The diverging lens diverges the rays from a distant object, an object at infinity, so that they appear to be coming from the actual far point of the eye. And then the eye can cope with them and focus them on the retina. So, what it must do, right, and in that case the diverging lens is diverging parallel rays. So what the lens must do is, or what the object must do, is an object at infinity is giving you, the rays are being diverged so that they appear to come from the focal point of the diverging lens. In other words, the object at infinity is giving you a virtual image at the focal point of the diverging lens, which is the girl's actual far point. So that's what's happening here. An object at infinity is resulting in a virtual image at the girl's actual far point, 400 centimeters. And since the object is at infinity, the image is at the focal length, therefore the focal length must be equal to the actual far point. Let's write that down. Where are we? Okay, so what is the power of the lens? Okay, so we can say that an object at infinity must produce a virtual image at the girl's unaided that's what I'm calling her actual far point. Which is at 400 centimeters. So object at infinity, virtual image at 400 centimeters. The object is at infinity, therefore the rays of the lens are parallel, therefore the image at 400 is at the focal point, and therefore the focal point, or the focal length, is 400 centimeters. Okay, but it's a diverging lens, so f must be equal to negative 400 centimeters. Because it is a diverging lens. Okay. Now, if the focal length is negative 400 centimeters, we can then quote power equals 1 over f. And in this case, we have to say the focal length is 400 centimeters, which is 4 meters. It's negative 4 meters. And that gives us a power of negative 0.25 meters to the minus 1, and meters to the minus 1 are known as diopters in optics. So the power of the lens is negative 0.25 diopters. Okay, now that bit is hard. I'll give you that. Okay, part 4 is harder. What is her range of vision when she's wearing spectacles or contacts fitted with this lens, which is this power of lens, negative 0.5 diopters. So we want her range of vision. Okay, well, when she is wearing the lenses, or when she's wearing the spectacles, that's going to allow her to focus an object at infinity. So her far point is now going to be infinity. So with glasses or spectacles or lenses, I'm going to call them spectacles, our far point is now at infinity. Now, without the glasses, in other words, unaided, her far point was at 400 centimeters. That's her actual near point, or our unaided far point. Unaided far point, yeah. Okay, so without the glasses she can only see to 400 centimeters. With the glasses she can see to infinity. Now, without the glasses, her actual near point was normal. It was 25 centimeters. But when she's got the glasses on, how does that change her near point? What does it become? Okay. Well, I think it helps to sketch the situation here. So if we do the little eyeball drawing, there's her eye, and there's the eye lens. If we fit her with her glasses, here is the diverging lens. Now, where's my ruler? Okay. So, without the lens, her actual near point is at 25 centimeters. So the closest she can see is at 25 centimeters. So that means that rays of light would be able to be focused. But with the lenses in place, what's going to happen is we're going to get a bit mucky. Right, let me put it a bit further out. Here's her actual near point at 25 centimeters. Now, so she would be able to focus rays from the actual near point. But with the lens in position, what the lens is going to do is it's going to diverge those rays a little bit. So rays coming from the actual near point get diverged a bit. So they appear to come from a bit closer. Now I've messed this up. So that is our actual near point. So, so if the object was here, that is the actual near point. If the object was here, then she would be able to focus on it, and that would be okay. But with the lenses present, rays will be diverged. But if we push the object a little bit further out to here, so this is the object, and we push it a bit further out, then rays from that object will be diverged so that they appear to come from the actual near point, and then she can deal with them. So in that case, what we'll have is an object a bit further out and an image which is a little bit closer in at the actual near point. But because the rays don't actually come from that image, it is a virtual image. So what we're looking for then is we're looking for the position of a real object that produces a virtual image at her actual near point of 25 centimeters. So so we need, I'm going to write that down, we need to find the position of a real object that produces a virtual image at the girl's actual unaided near point, which is 25 centimeters. Okay, so if we have a real object out here somewhere and we're trying to find that, then the object distance is question mark. The image distance, V, is 25 centimeters, but the image will be a virtual image, so it must be negative 25 centimeters. The focal length of the lens, we've already determined, has to be negative 400 centimeters because it is a diverging lens. Okay, so to produce an image at negative 25 centimeters with this focal length, where must the object be? So we need to solve that using the lens equation. So lens equation is 1 over u plus 1 over v equals 1 over f. Over the page it needs v, I guess. Right, so 1 over u is question mark, v is negative 25, and f is negative 400. Okay, if I bring the 1 over 25 across to make 1 over u subject, that will be equal to negative 1 over 400. But if I bring 1 over negative 25 across, the negative changes to a positive, so it becomes positive 1 over 25. Now, the lowest common denominator for 25 and 400 is 400. So we have negative 1 400th. 1 25th is 16 400ths. So that's plus 16 400ths. And that gives us negative 1 plus 16 is 15 over 400. So 1 over u is 15 over 400. If we flip the guy, that's 400 over 15. And 400 over 15 is 26.7 centimeters. Okay, so the object will have to be at 26.7 centimeters. What that means then is that if an object is at 26.7 centimeters, that will produce a virtual image at 25 centimeters in the diverging lens, and her eye will then be able to resolve that virtual image into a real image on her retina, which she'll be able to perceive. Okay, so what's happened is that with the lens, her near point moves out from 25 centimeters out to 26.7 centimeters, which is not that big of a change. Right, so to summarize then, with her diverging lens of focal length negative 400 centimeters, the girl's range of vision is from 26.7 centimeters to infinity. Okay. Now, without our lenses, the range of vision was, or is, from 25 centimeters because she's myopic, so she's okay up close, but it only went out to 400 centimeters. So without correction, her range of vision is 25 to 400 centimeters. With the lenses, it's 26.7 centimeters out to infinity. So she's lost a little bit of her near sight. It's pushed her near point out a little bit, but not much. But her far point has been pushed out from 400 centimeters to infinity. So that's hugely expanded her range of vision. So the gains outweigh the losses, I suppose. Okay, and that's that. Let's just review very quickly then. So if the near point was 25 centimeters, the far point was 400 centimeters, she is short-sighted or myopic, therefore she needs diverging lens. Then it gets difficult. We had to consider that if we want to, the diverging lens must mean that if an object is at infinity, it must produce a virtual image. It must place the virtual image at her unaided, her actual far point of 400 centimeters. Now, in that case, because the object isn't at infinity, that means that the rays are parallel. That means that the image is produced at the focal point, and that means that the focal length must be 400 centimeters. And we make it minus 400 centimeters because it's a diverging lens. Then power is the reciprocal of focal length in meters, and that gave us negative 0.25 diopter. Okay. Then could we calculate her range of vision? Well, with the spectacles, we've now seen that her new far point is infinity compared to her old far point, or actual far point, or unaided far point of 400 centimeters. Where is her new near point? So what we say then is that a real object placed in front of her eye must produce, or will produce, a virtual image at her actual near point. So therefore her image distance is negative 25, the object is unknown, and that's what we want to find. So we apply the lens formula and we come up with 26.7 centimeters. So that means that her range of vision with the lenses is now from 26.7 centimeters, that's her new near point, or her corrected near point, to a corrected far point of infinity. And that's that.